Welcome to Spring LIB.
Okay, we're looking at question 2856, where we have 2 point charges, Q1 and Q2, that are moving at different velocities. So Q1 is located at point 0, 0.25 meters, 0. So that's just right up on the y-axis here. And it has velocity 9.2 times 10 to the 5 meters per second in the I hat direction. And the I hat direction is the positive x direction. So that's going to be pointing straight to the right like this. Now charge 2 has a charge of minus 2.9 times 10 to the minus 6 coulombs. And this is coulombs. And it's moving with velocity minus 5.3 times 10 to the 5th meters per second. So that's in the j hat direction. So j hat direction is the y direction. So since it's negative, that's going to be going in the minus y direction like this. And it's at 0.1500. So that means it lies at 0.15 meters on the x-axis. And the other 2 coordinates are 0. So we're asked, at this point, what are the magnitude and direction of the magnetic force that Q1 exerts on Q2? So to solve this, we're going to need our equation that the force is equal to QV cross B. And when we think about this, we want the force that's exerted on Q2 from the magnetic field from Q1. So this magnetic field is going to be the magnetic field coming from Q1. So here we want Q2 and V2 to be what we're considering here. Now this magnetic field, this B will be B coming from Q1. So here's the expression for the magnetic field from a moving point charge. So here again, we're talking about Q1. So we're going to need to put in Q1 here, and again, V1 here, because we're talking about this point charge creating a magnetic field that Q2 is going to experience. So at this point, Q2 is a distance r from Q1. So I have listed that over here. So our first step is going to be to figure out what r is. So we have a nice little triangle here with the x coordinate is 0.15, the y is 0.25. So we can use the Pythagorean theorem where we know that r squared is just going to be equal to 0.25 squared plus 0.15 squared. And when we plug that in and solve, we can get that r is going to be 0.29 meters. So we have our r now. Next what we need to do is think about this cross product. So we have our r here for r cubed, but we need to know this v1 cross r. So we know the direction of v1 and we know the direction of r, and we know the magnitude of r. But the cross product, these 2 vectors aren't going to be perpendicular. So the cross product is going to be equal to v1 times r times the sine of this angle here. So if we label this angle, let's call it phi. So this is this angle phi right here. Now our expression for the magnetic field can be written here in terms of v1 times r times the sine of this angle phi. So now and before we actually get into this, let's just see quickly that there's a factor of r up here and a factor of r down here. So I'm just going to quickly cancel out one of these factors and turn this into r squared, just while we have it here. So now we need to know what sine of phi is. Well, sine of phi, if you look at this angle, we could make another triangle by just drawing a line right over here if we wanted. So this makes a triangle. This triangle that we're going to make, the opposite angle, so remember that the sine of the angle is going to be the opposite side divided by the hypotenuse. So the opposite side here is going to be our y component, which is 0.25, and the x component is going to be, the hypotenuse is going to be our value of r, which we just found up here. So the hypotenuse will be 0.29. So we know we don't even necessarily need to calculate this out. We'll just be able to plug this in right away here. We know that this will be our value of sine of phi. So finally, when we come here to plug this all in, we're going to have the force is equal to Q2 V2 cross B. So I'm just going to plug this whole thing in right here for B. Now, again, we have a cross product that we're going to need to deal with. So first, let's think about the direction of the magnetic field at this point where Q2 is. So again, to find the magnetic field, we had to take the cross product of V1 and R. So if we use the right-hand rule, taking the cross product of V1 and R, which is going down, that gives us a field that's pointing into the plane. So that's the negative z direction, or the minus k hat direction. So I'm just going to put that here so that we can keep track of that. This is the minus k hat direction. So now when we come over here and look at V2, V2 is going in the minus j direction, the minus y direction. When we take the cross product, we want to do V2 cross minus k, and that's going to give us the value of the direction is going to be in the plus x direction, or the plus I hat direction. So now we know our directions here, which is good. And remember, keep in mind, since the minus k hat direction and the minus j hat direction are perpendicular, the cross product, we don't have to deal with the sine of any angle, because the angle between those will be 90 degrees. So will be the sine of 90 degrees is 1, so we don't have to worry about taking any additional sines of any angles. So when we finally take a look at this, again, we can just get rid of this cross product because we took care of that calculating the direction, and the sine between the two angles is 90. We now have this whole expression that we can just plug right in. I'll just rearrange it a tiny bit to make it a little bit easier. But essentially, at this point, all we have to do is just plug in numbers. We have Q2, we have V2, we have Q1, we have V1, and we have sine of theta we found right up here, 20.25 divided by 0.29. R we already found. And we found the direction. So finally, when we plug these in, one more note about the signs, the positive and negative signs. We've already taken care of the directions of V1 and V2 because we took those into consideration when we were doing the cross product. But we have not yet taken into consideration the direction of, or the sign of, the two charges. So when we plug in V1 and V2, we want to use just the positive values. So we want to use just positive 5.3 and positive 9.2. But when we plug in Q1 and Q2, we do want to save these this negative sign here in Q2 because we haven't yet taken into account the fact that Q2 is negative. So when we plug this all in, we should end up with a minus 6.96 times 10 to the minus 6. And again, this is the I hat direction. So what this negative sign does is essentially says that since Q2 is negative, instead of having a force in the plus I direction, it's actually in the minus I direction, minus I hat direction. So we have a force with magnitude 6.96 times 10 to the minus 6. This is in newtons. Let's put that here. Let's indicate that here. This is in newtons. And again, it will be in the minus I hat direction, or the negative x direction.